Hello, and welcome back to Introduction to Genetics and Evolution. In the previous video, we talked extensively about population growth rate. I identified for you the intrinsic rate of population increase, and that is the birth rate minus the death rate. For most species, the birth rate tends to be much higher than the death rate, meaning the capacity for growing is very high. In this video, I'd like to introduce to you the concept of carrying capacity. That is the maximum number of individuals that can be supported in an environment the way it is. Now, I showed you this slide previously. This is looking at human population growth over the last several thousand years and projecting into the future. And you can see human population growth is very high. Our birth rate greatly exceeds our death rate presently, and you can see this by this increase in number of individuals over time. Now, our growth rate has slowed since the 1960s, 1970s, so meaning that the difference between the birth rate and the death rate has gone down, but it's still positive. There still are more people born than are dying. Now, intrinsically, this is not a problem, but what if there are not enough resources to sustain everybody? Well, this again ties into that concept of carrying capacity, which is often abbreviated as K. Now, this is the total number of individuals that can be supported within a population. Well, what determines this carrying capacity? What determines how many people can be supported in a population? Well, the answer is it's determined by the environment. Now, the question is, what happens when you exceed this carrying capacity? What happens when you go too high? Well, there's two things that can happen. The number of individuals that are present cannot be supported. So either you have to have a very sudden decrease in birth rate, that everybody holds back reproduction. That typically doesn't happen in most species. Or you can have, unfortunately, an increase in the death rate. So let's think about the impact of human population growth. Now, our world population already exceeds 7 billion people. Now, most of this growth, as I mentioned, has come about and is sustainable so far because of increases in hygiene, in medicine, etc. So, and also additionally to that, we are much better at producing food, and etc. And technology has compensated and has prevented these mass famines. There are still some famines in some parts of the world, but technology has definitely helped. But the question is, how long will this last? For many years, people have talked about a population bomb, that at some point in time we're going to hit the wall. Now, again, technology has staved this off for part of the world, but not all of the world. What's going to happen next? Well, let me ask a different question first. Why haven't we all starved yet? Why is it we were able to get all the way above 7 billion? Well, again, so far, food production, and this is averaging across the whole world. Again, some parts of the world don't have this. Food production has increased faster than population increases. That food production has actually increased threefold, while population has only increased twofold in the span of this figure here. Now, that can only work to a certain degree because the food that we're using can only be produced so fast, and we're continuing to reproduce at very high levels. So let me give you a problem to try. Let's use the formula I gave you before. N sub t, which is the population size at time t, is equal to n sub 0 e to the rt. Let's say the current world population is 7 billion. Let's pretend I just made this number up. The carrying capacity of the Earth is 20 billion. And let's say that's a future carrying capacity. And let's say that R is 0.012. That's the difference between the birth rate and the death rate. How many years until we have massive deaths? Well, I think that was a pretty straightforward problem. Again, we have the formula. N sub t equals n sub 0 e to the rt. Now, what we're looking for is this getting to this carrying capacity, and we'll say that's the time we're looking for. So n sub t then would be 20 billion. That's the carrying capacity we identified. N sub 0 is 7 billion. That's approximate for the current population size. Not exact anymore, but it's close. And R is equal to 0.012. Well, we put in all the numbers just as we had before. 20 billion equals 7 billion e to 0.012 t. So let's solve this out then. We divide 20 billion by 7 billion, and we get from that 2.85 is equal to e to the 0.012 t. Okay, so all I did was divided 20 billion by 7 billion. That's how I got this. So I take the natural log of both sides. The natural log of 2.85 is just a little bit over 1, so that would be 1.05 is equal to 0.012 t. Okay, now I divide both sides by 0.012, and what I get is t is equal to about 87. So 87 years. Now, I assume the world can hold 20 billion people. That may or may not be true. That may be a high estimate. maybe that's more than can actually be supported on the Earth. Could be a low estimate, but 87 years until we start seeing massive deaths. Well, is it going to be massive deaths? Well, what happens when we hit the carrying capacity? Well, one possibility is we may see a sudden crash. So this is a typical graph you'd see where you exceed the carrying capacity and then boom, the population goes down. And it goes down dramatically. So what caused this would be a lot of people dying. This has been observed in some cases. This shows, as it depicts over here, the population of the St. Matthews Island reindeer herd. We saw this dramatic increase in numbers and then a very sudden loss of resources and boom, crash down. That was very unfortunate. You may also see a leveling off. You may see it goes up and then it comes down a little bit and it oscillates, stays around the carrying capacity. This was observed in some classic studies using paramecium, where here's P. caudatum or P. aurelia, that it would increase to a level and then it would level off. Now, leveling off sounds good, leveling off at a carrying capacity, but you have to think of what does this actually mean? When you level off, you're either having a decrease in birth rate. I'm not sure if you're actually going to have that. The alternative is you're having an increase in death rate. That is obviously less positive. Now, you may see different outcomes in different places. Maybe in some parts of the world you would actually have a decrease in birth rate enough to level it off. Other parts you may see an increase in death rate. But this leveling off, or what's often referred to as the logistic model of population growth, is not necessarily a very good thing to happen. I mean, it's good in the sense it stops population growth, but it's bad in that it often means we're having an increase in our death rate. So if things are remaining unchanged at some point in time, the human population growth will exceed our ability to support that growth. So what do we do about this, or what do we do next? Well, there have been some proposals of what to do, and I mentioned the one-child policy, which was an attempt to decrease the birth rate. There have been more disturbing ones, though, too. So Ronald Fisher, who is the person who actually invented the analysis of variance test, Ronald Fisher suggested in his 1930 book, and this is a very disturbing proposal. The most obvious requirement for a society capable of making evolutionary progress in accordance with its current needs is that reproduction should be somewhat more active among its more successful than among its less successful members. It's a direct quote from his book. So basically, he was advocating, as he put it himself, a moderate superiority of upper class fertility. That basically we should let people in the upper class reproduce more than people in the lower classes. That is a very disturbing proposal, one with which I don't agree at all. We'll come back to this thing though later in a later lecture, which is referred to as evolutionary applications and misapplications, with emphasis on that latter point. Now, you may be wondering, how accurate is this math? I mean, I just gave you a bunch of numbers there. That looks a little scary, but is this actually meaningful? Well, there are some assumptions. One of the assumptions is assuming constancy. It's assuming that the intrinsic rate of increase doesn't change. And we know that's not always true. And we know that, again, the rate of increase is not the same in all different populations. When you look at the developing world, for example, the rate of increase is much faster than in the developed countries. And what this is showing you is an age pyramid. On the left side of each line here is the number of males. On the right side is the number of females, and this is population in millions. And the y-axis here is age. So in this case, there's a lot of very young individuals, not so many old. In developed countries, we tend to see fairly even distribution of age. There's about as many 60 to 64-year-olds as there are 20 to 24-year-olds. And you can see this by the numbers too, that in sub-Saharan Africa, 43% of the population is under age 15. In contrast, in Europe, only 16% of the population is under age 15. Same sort of difference when you look at the older ones. In Europe, 16% of the population is age 65 or older. In sub-Saharan Africa, it's only 3% of the population. So this is going to affect the rate at which populations are increasing. And the numbers I gave you are assuming this constant age structure, which you won't necessarily see. You'll often see this difference between rapid and slow growth. The other thing is that carrying capacity can change. Right? So you can have innovations in farming. That would be a positive change, where maybe those innovations will allow more food to be produced than was able to be produced before. That might raise the carrying capacity and stave off the problems. In contrast, you could have depletion of non-renewable or less renewable resources. That would be very negative. And that's probably what happened in the context of those island reindeer that you saw before. That there was some resource that they were consuming, and once it was consumed, it was gone. And it was gone not such that it could just come back the next year, but it was gone for quite some time. That could dramatically reduce the carrying capacity. And it could cause it to start at one place and then in future generations be much, much lower. So you'd have a much more severe crash than you would otherwise. You could also have other changes in the environment that again, make it so you cannot support as many individuals. Some species, as we mentioned, exhibit these booms and busts, while others have more of a cyclical process. So again, this is the St. Matthews Island reindeer herd. Went up very high and then crashed very, very hard. In contrast, this is the case of the lynx and hare in Canada. And we see these population cycles that, rabbits become very abundant, lynxes eat them, lynxes become very abundant. After lynxes become very abundant, the rabbits are mostly gone. Lynxes crash. The rabbits then grow after lynxes crash. So you have this, booms and busts over and over again. Honestly, we don't know what's going to happen in the future. And, these are all just possibilities that we're looking at. The important thing here is we can mathematically show that this is something to be aware of and concerned about. And ultimately, the math isn't perfect, but it's a starting point, just as I said before in the context of heritability. And this is informative for particular circumstances or for generating. Thank you for your time. I hope this was interesting.